All right, here is a helper video for the worksheet Kinematics and Total Distance Traveled worksheet. These problems come from old IB tests, so these are actual type of problems you would need to do on an IB test. So they're kind of tricky, but let's go ahead and think about it. Particle A is moving along a straight line such that its displacement from point P after t seconds is given by blah, blah, blah. This is shown in the following diagram. Okay, so this is its actual displacement. So when we talk about this, at time 0, it's going to be up here. So the displacement are basically, we're talking about a particle is moving along a line and it's moving in relationship to, say, a point. So say the origin is where a point is. So let's go ahead and start going to the questions. Another particle B moves along the same line. I'll come back to how the particle is moving. Along the same line, starting at the same time as particle A. The velocity of particle B is given by this. So we have a position function, so it's displacement function, and we have a velocity function. But these are for two different particles. So there's two things that are moving around, and they're moving on a straight line. So notice that this up and down business is created by time moving. So if you think of the particle moving in relationship to the origin, so say here's the origin, I have this object, it's perhaps starting at a distance away from a point. So this is the distance away, right here is the distance, how far away it is. So it's starting at a certain distance away, and then it's going to get closer to it. So it's going to get closer to it, and then it's going to go past it, and then it's going to come back towards it again, and it's going to, again, go past it, and then it's going to turn and go towards it again, and then it's going to keep going. So this is one way of thinking about it. I have some object here that a particle, again, it's starting here, sorry. It's starting at some distance away. This is the distance away. This height here is the distance to the point. So it's getting closer to the point, and then right here it passes the point, and then down here it turns around and starts coming back towards the point, and then here it turns around again and starts going back towards the point. It passes the point right here, and then it keeps going away in the other direction. So this is kind of a diagram of what's happening, but it says that it's in a straight line. So if I were to put this on a straight line, it was starting some distance away, it comes towards the point, it passes the point, it turns around, it comes back, and then it turns around again, and then it goes back and keeps going. So if it's in a straight line, that's what it would actually look like. If we were actually looking at the particle and its position in relationship to a point, that's what we would see. We would see something coming towards this point, passing it, turning around again, and then keep going. But I sort of broadened it out a little bit here so you can see it going past the point, here's the point, going past the point, turning around past the point, turning around past the point, and keep going. Okay, the reason why it looks like this on here is because it's spread out, because this is happening over time. So I just wanted to give that sort of idea of what is happening with our particle. So find the initial displacement of particle A from point P. Whenever they say initial, they're talking about when t is equal to 0. So here is our function right here. You want to substitute back in, you want to substitute into that when t is 0. So you want to put t is 0. So what I would do is I would enter this whole thing into my graphing calculator, and I would use the value function. Okay, so if I think I already put it in here. Yeah, so I already put it in. Sorry, I keep sniffling. I hope you can't hear that so loud. I would put in 15 minus x. I use x for the t because, of course, our calculator, you just use this button right here. Minus 6x cubed, because I'm using x for the t, e to the negative 0.8x, which is the t. And then I can evaluate it by using the calc menu, and I can just say I want the value when x is 0. So I'm going to put in 0. Oops, what happened? Did I not select it? Oh, it's still thinking. Sorry. I'm moving too fast. Okay, when x is 0, where t is 0. So when t is 0, what do we get? We get 15. So that means this distance here is 15. So it's starting, right here, it's starting at a distance that's 15 centimeters. So the distance, the original displacement, is 15 centimeters. Okay, and we can put that there as well. Find the value of t when the particle first reaches point P. So here's point P. So remember what I was saying? It's starting 15 centimeters away, it's coming down, it's passing it, it's turning around, passes it, turns around, and then keeps going. So when does it first pass it? It first passes it when the displacement is 0. Where's the first place that the displacement is 0? That would be right here. So find the value of t when particle A first reaches point P. It's first going to reach point P right here, because the distance, this is the distance is going to be 0 right here. So what time is that? So we need to find our X-intercept. So again, I can use my graphing calculator. So I'm going to go to calculate, and I want the zeros, and I want this one right here. So get my left bound, get my right bound, and what does it say? It says 2.4694173. That's when y is 0. So I want to know when is S equal to 0, because this is S on my graph. When is S equal to 0? When t is equal to 2.47. 2.47 seconds. That's my time. Okay, find the value of t when particle A first changes direction. Okay, so we can see that on the graph. You can see how it's going. It's going, if we think about this as up and down, it's going down, 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 and then it goes up, 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 and then it goes down, 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 down. So where is it first changing direction? Right here. This is where it's first changing direction. Okay, if we think about that in terms of the particle in point P, over here, I'm going towards point P, I go past it, and then I turn around. But yeah, that's right here. So find the value of t when particle A first changes direction. Well, that would be a minimum. See, that's at my minimum right here. At the minimum is where it's changing direction. So let's, oops, clear that out. Let's find the minimum. So again, graphing calculator. This is my best friend. I want the left side of that minimum, and then I want the right side of that minimum, and enter. And I want the value of t, so t is my x. So it would be at the minimum. The minimum value here is where it's going to be changing direction. That is at t is equal to 4.08. Again, I'm using 3 significant figures. Okay, and that would be seconds. Find the total distance traveled by particle A in the first 3 seconds. Okay, so in the first 3 seconds, from here down to here, how long did that take? That took more than 4 seconds. So 3 seconds is actually somewhere, let's get my graphing calculator, 1, 2, 3, it's like right here. So the total distance is going to be this distance here plus this distance down here. So we know it started at 15 centimeters away. So I know from here to here back to point P, because remember again, it's on a straight line, so it's going towards point P. It reaches point P right here, and I know that that distance is 15 centimeters because the initial time to the time that it's at P, we used our equation to figure out how far away it started. So I know this is 15 centimeters. And then I just need to figure out from here on down to here, how far is that going? So find the total distance traveled by the particle. I just need to figure out where is 3 seconds on here. So I'm going to use my calculator again. I want to find the value. So calculate value when time is 3 seconds. It's right there. So at 3 comma, it's like, looks like it's about halfway down here, right here. This is at 3 seconds. It is at negative 2.69638. Oh, sorry, you can't see that off the side. Negative 2.696308. So I can just take that to the, I'll take more than 3 significant figures for right now. 2.696. So if we're talking about distance, right, I need this distance plus this distance. So this is kind of like when we're finding area under a curve and part of the area is underneath the x-axis. I need to take the absolute value of this. Okay, so this little distance right here has a distance of 2.696. So the total distance is going to be this part plus that part. Okay, there's probably other ways you could have gotten this answer, but this is just how it makes sense to me. I want the distance from where it started to point P and a little bit past it. So I need to add this side and I need to add that side. So I need to add the part above and the part below. Okay, so my total distance is going to be 15 plus 2.696. So if I add those together, oops, gotta quit out of there, 15 plus 2.696, 17.696, and round that off to 3 significant figures, that's going to be 17.7. So my total distance is 17.7, and that would be centimeters. All right, given that particle A and B start at the same point, find the displacement function for particle B. Okay, so this is where particle A started in relationship to particle B, P, and particle B is going to start there also. So it's also going to start at 15 centimeters away. Okay, so it's also going to start 15 centimeters away, but it's all we know about it is how fast it's going. We don't know exactly where it is. We only know how fast it's going, and we know its starting point. So we know its starting point is also here at 0,15. The particle B is also going to start here. Particle A and particle B are going to start right there. All right, so find the displacement function. So we have the velocity function. So the displacement function, and they're calling it S sub B. So S sub B of t is going to be equal to the antiderivative of the velocity. Okay, so because if we take the derivative, of the position function, starting to go off the bottom, we will get the velocity function. So if we want to go backwards, I know the velocity function, I'm going to have to integrate it to get the displacement function, because I know this, but I don't know this. If I knew the position function, I could just take its derivative to get the velocity, but I don't know the position function, I know the velocity function. So that means I'm going to have to integrate v of t in respect to t. So notice how we're usually writing dx here. I'm writing dt because our variable is t. I'm going to be taking the antiderivative in respect to t. All right, so what is my velocity function? It's right here. So I'm going to integrate 8 minus 2t dt. So this is a pretty straightforward integral. This is going to become 8x minus, oh, not x, sorry, t, 8t. The t, I have to add 1 to the exponent, multiply by the reciprocal, and I still have that times by 2. And plus c. So, oh, I don't have, I don't have any boundaries on this. So I'm just going to leave it as an indefinite integral. Indefinite answer. So this is going to be 8t minus t squared plus c. Now, I want to find the actual function. So this is S sub b of t. This is the displacement function. Okay, we started with the velocity function to find the displacement function. This is how I'm going to write the displacement function of b. I can actually solve for c because I know a point on this function. I know that this function starts at 0,15. So I can plug in 0 for the t And the value of the function needs to be 15. So I can say, okay, I know that the value of the function is 15 when t is 0. And lo and behold, these go away, and I'm left with c is equal to 15. So if you know your y-intercept, if you know your starting value, that is your c. Yay, I just found c. Okay, so I can now write my displacement function. So let's squeeze it in here. So my displacement function of particle B is equal to 8t minus t squared plus 15. There it is. Now, find the other value of t when particles A and B meet. So I want to find out when they meet. I now have a displacement function for B. I have a displacement function for A, and I have a displacement function for B. I want to know when are they in the same place at the same time. So we want the intersection of these two curves. So I could do it by hand. I could say, okay, I want to know when SB of t is equal to SA of t. And I know SB of t is 8t minus t squared plus 15. And the displacement function of particle A was given to me. That was the first equation I was given, minus t minus 6t cubed e to the negative 0.8t. And then I could try and solve that by hand, but that looks really hard. Hence, graphing calculator. So I'm going to go ahead and enter the second equation, the displacement function for B, into my calculator. So I have 8x minus x squared plus 15. So now I have them both in there. Let's go ahead and graph it. We should see them starting at the same place. See how they intersect there? Oh, there's the other intersection. That's the second time that they meet. So I'm going to go ahead and find that intersection. So I'm going to go over towards that intersection, move my cursor over next to it, hit enter again, and enter a third time, and it'll give me the intersection. So find the other value of t when the particles meet. I only need the t value, that's my x, time is my x, so I get 9.30. So the time is equal to 9.30 seconds. Okay, so one thing I want to point out is that we use the graphing calculator for pretty much everything. And so one thing that I've noticed is one way of drawing attention to this, for example, if you're taking the test, you could put by graphing display calculator. So all of this stuff, we got all of it by the graphing display calculator. Same thing here, by graphing display calculator. So what was important is I'm like saying, what am I putting into my calculator? I'm looking for when time was 0. I'm looking for when the value of the function was equal to 0. I'm looking for the minimum value. So I'm writing down what I'm looking for, and then I'm putting down the answer. Okay, and then the distance, I also can show it on the graph. So you definitely need to show work, but the number crunching is being done by the graphing calculator. And so the way that you can show that is by saying by GDC, graphing display calculator. All right, I'm going to take a pause before I do the next problem. What I want you to do is the next problem is actually simpler than the first one. So I want you to try and do this problem without me, and then watch the video after you've tried it to see if you got it right. And also, you know, there's more than one way to do things. So if you got it right using some slightly different method than I did, fabulous. As long as you can justify your method, that's fine. Okay? Signing off, and I'll start another video in a minute.